Hi, this is Yukai from National Yangming Chiaotong University. We are happy to present our research, asynchronous state estimation of simultaneous equal motion estimation and multiple object tracking for LiDAR inertial odometry. In this work, we propose an asynchronous vector graph formulation for LiDAR inertial odometry, which is called LiDAR segment. So what is segment? Given a real-world example, we would like to estimate the equal motion, that is the robot trajectory. Here we can see some moving objects. And the main idea is to simultaneously estimate the robot trajectory and those moving object trajectories. LiDAR segment is formulated under the asynchronous update mechanism so that robot states and object states are truly estimated over time. In our real-world experiments, LiDAR segment can provide accurate odometry results and continuous object tracking results. In developing the segment solution, we observed that most well-known odometry approaches adopt a keyframe selection mechanism for efficiency. In this way, only keyframes have their corresponding states in the vector graph, and the other frames are directly removed from the system. If we only use them to check surrounding objects, you can see that some object detections are also removed. And thus, object states cannot be truly estimated based on complete measurements. Also, the odometry system cannot benefit from high-quality cues about object tracking. It motivates us to conduct the research of formulating an asynchronous state estimation method. So, given IMU and LiDAR measurements, the odometry part of LiDAR segment inherits LiDAR SEM. In this vector graph, xt is the robot state at time t. Between two consecutive robot states, there are two vector types representing LiDAR scan matching results and the relative transformation given by IMU pre-integration, respectively. Then we introduce the object tracking part of the proposed vector graph. XTI and the VTI represent the number of object pose and the velocity at time t. There are three vector types related to object tracking. The first type is a constant velocity vector. It constrains that object velocity should be stable. The second type is the smooth movement vector. It formulates the object motion based on the previous object pose and the velocity. The third type is the detection vector. It provides measurement constraints for the object poses, in which object detections are given by LiDAR-based 3D object detection methods. So far, this is a synchronous LiDAR segment because moving objects have the same update rate as a robot state. Now we are going to explain how the asynchronous version works. We would like to put object states and vectors related to non-keyframes to the vector graph. Taking a subgraph for example, we put those object states to the vector graph first. Then we add new detection vectors to the vector graph. Those vectors refer to the mark detection measurement model. It's called mark detection because the detection is transformed from non-keyframe to the last keyframe, and we viewed it as a detection of that keyframe. It makes non-keyframe moving object states be constrained without adding corresponding robot states to the vector graph. With that, we obtain the asynchronous LiDAR segment. We use two real-world datasets to evaluate LiDAR segment. The first dataset is the well-known Kitty dataset. The second dataset is a self-corrected Hsinchu dataset. It's a high dynamic environment because there are many moving objects. This is a demo video with a Kitty sequence. We can observe that the synchronous version doesn't output complete tracking result, but the synchronous version does in this case. In quantitative analysis, we can see that a synchronous LiDAR segment presents better odometry results than the synchronous version, as well as the baseline model LiDAR SEM. As for object tracking, the asynchronous version also outputs better tracking results than the synchronous version. Now we move on to the Hsinchu dataset. The robot is stationary in the beginning, so there is only one keyframe in the vector graph. You can see that we do not have up-to-date object tracking results in the synchronous version, but we have in the synchronous version. Furthermore, the lack of detection information may affect the quality of object tracking, consequently disturbing the odometry. In quantitative analysis, we also find similar observation as in the Kitty dataset. We also compare the computational time of the three methods. LiDAR SEM does not compute object tracking, so it takes the shortest computational time. Asynchronous LiDAR segment additionally computes object states in non-keyframes, so it takes the longest computational time. We also see a very large computational time of Lao segment in Hsinchu dataset because it contains a lot of moving objects. In summary, this is an odometry approach to estimate LiDAR inertial odometry and multiple object tracking asynchronously. Our experiments indicate that Lao segment present accurate odometry and object tracking results in dynamic environments. In the future, we would like to speed up Lao segment with a multi-route ISM2 approach. Also, we would like to explore the global optimality of Lao segment with a generalized mixed integer programming. This is the end of my presentation. Many thanks for your attention. If you're interested in our work, please refer to our paper and code.